we reached till velocity profile, right? This is where we were. So we figured out that the velocity distribution as a function of y, or the between the direction of the film thickness. This is y, which varies from 0 to h, which is the film thickness, right? So the variation is basically a function of pressure gradient and the location y. So basically u is 1 over 2 mu dp dx, which is the pressure gradient, y square minus hy, u plus u divided by hy. And if gradient is 0, then it will be uhy, which will be a straight line like this. If the gradient is negative, less than 0, then it will be something like this. Let me just delete it. Looks like, so this is the negative gradient. This is the negative gradient, and this is the other way around. So this is the positive gradient, and this is the negative gradient, and this is how the distribution of u would look like. Now, why did we find u? So we wanted to find something. The idea was that we want to find a governing equation which will predict the film thickness and the film pressures. That is the idea. So film thickness, what will be the film thickness and the pressures? This is what we want to do. So now once we have this this u, we said that what we can do is, we know that the entire flow will be basically, I can go u dy 0 to h, and whatever, so basically this is u dy, but then we assume that there is unit. This is for unit thickness or z, unit z. If the thickness is unit, this will be, q will be 0 to h u dy. So now let's find what will be u. We know what the u is function of y. So let's just go ahead and then see how do we get that. Let me just show the Mathematica real quick. So we will integrate it. You should see Mathematica really soon. So this is what we found for u as a function of y. Let me just go ahead and blow it up a little bit. So this is the q. If we do for unit thickness, we could actually not thickness, but unit depth, if you'd like to say. And then this will be the flow will be. I can basically find a total flow which will be 0 to h u dy. Let me just go ahead and do it. Oh, sorry, my mistake. Let me just, there was some point. Clear the variables and then it will do it. Yeah. So basically what you get is, you get hu divided by 2. dp dx, I have assumed it to be the pressure gradient, which is not a function of y. Right. So that's why I have used it as a pressure gradient. And then h cube by 12 mu. So basically, let me go ahead and switch to my writing tablet. Just 1 second. Let me go ahead and okay. So basically, okay. So this is what you see here. Let me go ahead here. So this is where we were. This q was u dy. We found out that u is nothing but u h over 2 minus h cube by 12 mu dp dx. This is the pressure gradient. Now, can somebody tell me that what will be q as a function of x? So basically, I'm assuming that the fluid is flowing into a converging gap, right? So what will be q at every location? So this is x direction, the direction of flow. and this is Q at every location. This is Qx. Will Qx change as a function of x? Any questions? You can type in that or talk to me or type in the chat box. Will there be a change in the flow? Assuming this is incompressible. Anybody? Will there be a change in the flow? Yes or no? Will Q be constant as it flows through X? Yes or no? Somebody? So my fluid film is flowing through a converging gap, right? Now I know Q as a function of X. I have this Q as a function of X. Do we think Q will change as a function of X? Yes or no first, and if yes, why? If no, why no? If yes, why yes? Anybody? At least one of you should answer, right? What happens to the Q? Will Q change as so here say Q1 x1, Q2 x2? Will Q1 x1 and Q2 x will be different if the fluid is flowing? Somebody? I'm sure you guys have done this multiple times, right? You know this very well, right? Will Qx change or no? At least yes or no. One yes or no I should get from you, right? Okay. For compressible also what will happen is AV may change, rho AV will remain constant, m dot will remain constant for compressible. For incompressible it won't change. Correct, very correct. It will not change. Because why will it not change? Why will it not change? Answer is correct. It does not change. Q1 and Q1x, Q2x will be constant. But why will it be constant? Qx will be constant. Why? Mass conservation or continuity, right? There has to be continuity. Otherwise, if it doesn't then there will be separation of the fluid. Right? Flow will not be continuous. So this we assume that the flow is continuous. Otherwise, there will be these pockets which will be formed. Discontinuity will be there. So correct, very correct. The mass has to be conserved because you assume that there is continuity. Okay. Very good. So now I know that this is my equation and say dq dx to x. What will I get? I'll get u over 2 dh dx and 1 over 12 mu d by dx h cube dp dx. Right. If I solve it, I will get d by dx h cube by mu, or we can mu is constant, so you don't have to worry about dp dx is equal to 6u dh dx. This is the equation which is called Reynolds equation. This equation right here, it assumes that side leakage is not there. Side leakage means in the z direction through the thickness of the sheet. We are assuming that there is no leakage in this. There's no side leakage. There is no side leakage. Right. If side leakage is included, so what will happen is there will be two pressure gradients, one on the side of x, other side g. So it will become a partial derivative del x h q over mu del p del x plus del by del z H cube by mu del P del Z is equal to 6U dH dx. Now, if you solve this equation, there are two variables, pressure. The pressure value is the pressure is a function of x, and H is also a function of x. So you would need some more boundary conditions to. So it's actually a there's no closed form solution for this. So Reynolds equation is the single most important equation in the field of tribology. This equation which you see right here, the single most important equation in tribology. In tribology, there are books. It's like Navier-Stokes equation, but only true for film thickness. So you have to do film thickness and pressure. There have been people who have been solving this equation their entire lives. That's all they have done. They've used supercomputers to solve this equation. They have done all sorts of things. There have been people who have devoted 40 years of their lives just to solve Reynolds equation. That's all they have done in their lives, solving this equation. So I can't emphasize how important this equation is, because this is the foundation. This equation is the foundation for your fluid film lubrication. So fluid film lubrication is entirely governed by this Reynolds equation, and there's no closed form solution for it. So what people do is, there are analytical solutions that don't exist. So people will find numerical solutions for various conditions. They will find it first for full film, for mixed lubrication, boundary lubrication, all sorts of for different textures on the surfaces with the full film. So people do all sorts of very complex conditions and solve this equation, right? But a general approximate solution is that RC F is square. R is the radius of the journal. Radius. Journal meaning radius of the shaft. Or sleeve also you assume to be the same. And C is the clearance. So this RC over F is some function of R over C square mu n over P. And this is Sommerfeld number. Sommerfeld number. So what people have done is people have created whole bunch of charts of solutions. They have solved these equations numerically, and they have created charts as a function of Sommerfeld number. So basically, if you want to design a bearing, you have a viscosity, what fluid you are using for your lubrication, fluid viscosity. These are under your control. A designer has this under control. What is the load per unit projected area? So basically I have some load, and it is basically projected over, say, over this, say this is my shaft and this is my sleeve. So basically if I know the sleeve is 2R, so basically P will be W over, and this the length of the support is, say, L. So this is the sleeve and this is the shaft. This is total length is L. So basically what you'll have is P is equal to 2RL. L is the length of the support. The shaft can extend even more than that. Let me just show you some portion of the shaft. So basically if I have a shaft like this, and then I'm supporting this into sleeve. This is a cross section, imagine, right? So I'm supporting, so this length is L, this diameter is 2R. So my actual pressure will be W by, and the W is the total load acting on this journal, on this bearing, on say bearing 1. on say bearing 1. So W is the load supported by this bearing alone. So W by 2RL is what will be the pressure here. Okay. So pressure you need, this is also an important thing. Speed, RPM, at what speed this is rotating, that also is important. And then bearing dimensions. So what is the clearance? Clearance between the shaft and the sleeve. The radius, you know, radius of the journal. Beta is what is the angle on which is it 360 degree for the full sleeve, and how much is the sleeve dimension, sleeve angle. This is beta. Right, it can be open, it can be fully closed. And then L is the length, this length. How long is the sleeve? So these are the design parameters which the designer will specify while designing this bearing. Then there are dependent variables. Once you define all this, then there would be some dependent variables which will be coefficient of friction F, temperature rise delta T, fluid flow Q, and then H naught. These will evolve. These will evolve. These you do not have control. This you have control. Right. This will just an outcome of the, for lack of better word, outcome of the bearing action. So there will be some coefficient of friction because there will be a fluid film and this fluid film will resist the motion. So there will be some coefficient of friction. There will be some temperature rise because there is friction. So there will be some temperature rise, and there is some flow, oil flow, and there will be some film thickness which will stabilize after some time. Initially, it will be almost sitting on the top of it, but the moment pressure difference, the pressure generates. The pressure generates, there will be a physical separation. So once it starts to rotate, there will be physical separation. As I showed you in that example which Tower observed, right? The moment the shaft is to rotate in the rail bearing, the cork used to pop out. The cork used to pop out because pressure generation is there. And there will be a supporting film thickness. So there will be film thickness which will physically separate the shaft and the sleeve, and there will be pressure generation. So this pressure which you're talking about is just load per unit, but there will be also pressure in the film. That is a dependent variable. This pressure in the film pressure, which evolves is also a dependent variable. It is not listed here, but that is the film pressure which is in the film thickness. This is just the top P is just in your imagination, that's some average pressure bearing. But the film thickness itself will have some local pressure, which will get generated when the bearing rotates. We'll talk about it a little bit as we go along. So basically, how the angular speeds shape up is the journal can have rotation. The journal can have angular rotation. Journal meaning the shaft. This is for the shaft. The bearing can also rotate, right? So this is bearing. And then the loading vector, if the load is not, if there is, imagine their load is concentrated and the load also rotates, right? Or you have a physical load that rotates. In that case, your net N is not just the journal, not just the shaft rotation, but the shaft rotation Nj plus the bearing rotation minus 2 times the load rotation. Imagine a case when bearing is 0, load is 0, your N is nothing but just the shaft rotation, right? And if your NB is 0, bearing is 0, and NF, your NF is equal to Nj, meaning your general angular speed, your angular speed of your shaft and the load vector is same. In that case also, what will you get is general rotation. Okay. So that's how you get your values of N. So in a case where bearing is 0, your load is half the journal, then you will get 0 net angular rotation. So there is concept of net angular rotation, meaning if all three are rotating, your shaft sorry about that. Your shaft, bearing, and load vector. So you get a net N, and this is the N which you have to use in charts. I will actually show you today the charts. How do you go ahead and look up those things which are required? How do you determine the friction? How do you determine sorry, my mistake. How do you determine friction, H, which is the film thickness? So temperature rise, all this we have solutions for it. I'll show you how to determine all that. Okay, we'll get there. So basically, there is a Tumpler's design criteria which is very important. Tumpler is actually a bearing, he's a very well-known bearing designer. He recommended these set of design criteria. He said that these are the design criteria which we have to use for your applications. He says that minimum film thickness to prevent accumulation of ground of surface particles, because if you keep the thickness very low, what do you think will happen? If the film thickness is very small, what do you think will happen? If the film thickness is not very large, very small film thickness, what do you think may happen? Any answers? Somebody, if film thickness is very small, what do you think will happen? We talked about it, right? Take two limiting cases. In one, the film thickness is very small. In other, film thickness is very large. What will happen if the film thickness is really, really small? What do you think may happen? Somebody. What do you think will happen if you really create if you have really film thickness? Very good, very good. Asperity to asperity interaction. What will this asperity to asperity interaction do? If you have these asperity to asperity interactions, as you're saying, so these will interact with each other. So basically, let me do a much better job of it. If say something like this, if these are interacting, what will happen? These are moving. One is moving in this. Sorry, let me say that they're moving in other direction. There's a relative motion between the two. What do you think will happen? The high points will interact and do what? Yes. So there will be a lot of wear. So based on to avoid this wear, right, physical wear, we need to have certain minimum film thickness. This minimum film thickness is defined as 0.00508, which means 5 micron plus 0.000 charge 0.00004D and D in millimeter. He says that this is the absolute minimum you have to avoid that, right? And imagine these shafts which you know and bearings, these have sub-micron surface roughness. The surface rougnesses are below a micron. Sometimes it will be even 0.1, 0.2 micron or lower. Okay. So this is what he suggested, at least 5 micron plus of multiple of D, or the diameter which you are using. Then he suggested that your maximum temperature should be less than 121 degrees centigrade to ensure that nothing vaporizes. Your fluid film doesn't really vaporize. And then he said that there is maximum starting load, W start, by LD, which is the starting pressure, should be less than equal to D2068. Now you know why he is saying, why he has a separate rules for starting and operational. So this is only for starting. This is only for starting, not operational load. Right? Why would he keep starting so low? So your starting load should always be low. So bearing loads, if you want to understand, you should have some. So either you pressurize the fluid initially to make sure that there is some support, or you don't load it fully. So you don't provide the full load in the beginning when the bearing is started. So when you start, say, a thermal power station or a gas turbine, you do not load it fully. You will not apply it full load. You will start it in a very ramped up fashion. You'll ramp it up gradually. Why would you do that? Why would your starting load would be low? If it is not low, what do you think will happen? Yes, it's right. Damage the part and wear. Problem is the static and dynamic coefficient of friction. We should not think about that right now, because what happens is this is actually a special case where fluid pressure builds as a function of your pressure building is a function of your speed of u. H is a function of u, right? H and P both are a function of your relative velocity. So the pressure creation will happen only after you reach certain RPM. So what happens at lower speeds, there is no pressure in the fluid and the film thickness is also very low. So the moment once the fluid starts to flow in the converging gap at certain speed, the fluid starts to flow in the converging gap at certain speed, then only this pressure will kick in. There will be local pressure and separation. There will be local pressure creation and separation, pressure creation and separation. So don't think about it in terms of dry friction. This is not a dry friction. This lubricated friction is a different beast altogether. That's how you have a fancy Reynolds equation for that, which actually says that the fluid has to flow in a converging gap. And velocity, only there will be pressure and film thickness formation and film formation. And this film formation will support. So initially what you have to do is you have to not load it fully when the system is getting started. Most of the power plants which use gas turbine, which rotate at very high speeds, or very even steam turbine, they actually make sure that the bearing is loaded gently, right? Because these are general bearings which they use. So they will actually they will not start with the full load. They'll start with a very partial load so that the pressure is created. Once the pressure is created, then it will start to support full load. So you have to ramp it up gently and make sure that the load doesn't come at one go. Otherwise, there will be the film will not form and there will be this rubbing action and there will be a lot of wear, right? Heating, wear, a lot of undesirable things may happen. So viscosity is a function of temperature. We know that the higher temperature, it will be less viscous. But there is a solution by Raymondi and Boyd for Reynolds equation. They assumed constant viscosity to the loading zone. And then they used to find temperature is T1 plus delta T by 2. They used average temperature to find the viscosity. Okay. So these are the first charts, the viscosity charts. So these are for different lubricants. These are called SAE, Society of Automotive Engineers. Automotive engineers, because most of these things are used in vehicles, right? So there will be SAE, there will be SAE 70, 70. So basically these are grades of SAE. The higher the number, the greater the viscosity. And these viscosity actually at 10 degrees centigrade temperature, it's very viscous. This is a log scale. This is a log scale, not log scale. This is log only viscosity is in log scale. And you see there's a significant reduction in viscosity as you heat it. So viscosity lower means the film thickness will not be able to form, because mu is also an important part in film formation, film and pressure formation. You see, Reynolds equation has mu there, right there. Now this is the polar diagram of the, so this is, if you imagine, this is a general bearing, which basically means that fluid is flowing through this. This is the converging gap. So it starts from there and the gap starts to converge. There is a minimum film thickness. This H naught is minimum film thickness, and the material is flowing and the fluid is flowing through this converging gap. Fluid flowing through converging gap. Fluid flowing through converging gap. Through converging gap. So here the pressure will start to build up. You see, the pressure starts to build up. This is the film pressure. You see, it keeps on increasing, and P max is right before the minimum film thickness, just a little bit before minimum thickness, and then again the pressure starts to die out. So this is the pressure. This is the pressure which is there in the film. So the peak pressure is somewhere here, right here. So this pressure, and there is a there's a finite film thickness also. There are two aspects to it. One is actual film thickness formation. The film thickness changes. This is the minimum film thickness. Film thickness is changing as we go along, and the pressure is also increasing. The pressure, maximum pressure is very close to the minimum film thickness, but not at that location, slightly before the minimum film thickness. This is called P max. So the flow in the converging gap, the fluid flow through the converging gap does two things. Converging gap through converging gap does two things. What? Tell me. What does it do? 1 and 2. First thing, what does it do? The fluid from the converging gap, what does it do? It does two things. Somebody. Yes. So in that other order, I would say film is important, but more important is pressure generation. I think first task is it generates pressure between these two, right? The film has pressure. This pressure generation is the phenomenon which provides the bearing action. Phenomenon which provides bearing action. Because this pressure is what supports the load, right? And the second is film formation. Film formation is okay. If the film is smaller, if pressure is there, that's fine. The film formation actually is what separates separation is because of physical film formation, thick film formation. So these two things are important. Pressure generation is of key importance because that is what supports the load. And there is a film formation in there. And this is a stable film. So you want a stable film, you want a full film for lubrication so that the surfaces are separated with some finite amount of pressure to support the lid. And these support excessive loads. So these things are designed for very high loads and very high speeds. High speeds for which you don't have a rolling element solution. You don't have a rolling element solution for this. Rolling element solution. Right? Good. So let's move on to some next things. So these are some of the charts which we will see. I'll just go over the charts and then we'll do some problems to basically get a better feel of it, right? So I said that all of them would have something called Sommerfield's number, which is R by C whole square mu n by P. So for any condition, we need to find the Sommerfeld number. That's something which we will have to find. And then what we do is, and this is called bearing characteristic number or Sommerfeld number. And then what we do is, we need to have this L by D ratio. So L by D ratio would be, L is the length of your journal bearing, the length of the journal bearing, and D is the diameter of the journal bearing. So if you know that for different L by D ratios and the bearing number, say my L by D ratio, so say my bearing ratio is say 0.35, let's say, or let's say 0.4, take even number 0.4. So 0.4, sorry. So my bearing ratio is 0.4 and say L by D ratio is half. So I can find out what will be my H naught over C. So I can find out what is H over C. So these have come from people have plotted this by solving these Reynolds equations. Reynolds equations have been solved and people have plotted these results. Okay, and they have found out that HO over C is this. So C, we know the clearance, right? We know the clearance between the that's just the initial clearance. Once the bearing starts to rotate, there will be a physical film formation. So that will be, so I know the initial clearance and multiplied by this number, so I can find out what will be the H naught or the maximum film thickness. H naught is the maximum film thickness, right? And this is eccentricity ratio. Eccentricity ratio, if you want to see, is E by C. C again is clearance and E is the actual eccentricity. So I can find out what will be the eccentricity. If you want to go back, what eccentricity is, I'll just show you. This is eccentricity. This is E. And so everything will be function of C because it's a non-dimensional chart people have created. So it's E by C, H naught by C. These are non-dimensional parameters. So these are valid over wide range of parameters. People have solved a non-dimensional Reynolds equation, and then found out these values. Right? Any questions here? Do you have any questions? We'll do a problem and then we'll have better handle on this. Okay. Same thing about phi. This is the position of minimum film thickness. So where does the film thickness occur? This is phi. This is phi. From the vertical, where does the minimum film thickness occur with respect to the vertical axis? Again, everything is function of R by C square mu n by P. Then same thing, coefficient of friction. So friction, you dimensionalize by R by C, radius by C by F. So that's how you non-dimensionalize the friction coefficient. All right. And then you can find out how the friction coefficient will vary. So higher the bearing characteristic number, higher the friction. Maximum film pressure is again P by P max. Okay. So that the way you do it is P by P, you know, right? P, you know, is you get from your equation, it is W by 2RL. So you non-dimensionalize this by P max by P. P by P max is this relationship. And again, you do it with your Sommerfeld number or your bearing characteristic number. Let's do a small problem. So we know that we have to find, say, H naught and E. If my viscosity of my thing which I'm using is 4 micro Reynolds, RPM is 30 revolutions per second, W is 500 pound, R is 0.75 inches, C is 0.05 inches, L is 1.5 inch. So let's first thing is what we need to find first is average pressure P And then I need to find Sommerfeld number. Let's do that first. Sommerfeld number. Okay. What I will do is I will share my Mathematica. So this is what we know, right? The problem set. Let me just clear all the variables, otherwise it creates problems. So it says my load, which is supposed to do is 500 pounds. 500 pounds is the load. 500 pounds is the load. And then radius is 0.75. So basically diameter is 1.5. Clearance is 0.0015. That's and this clearance is concentric clearance between the journal and the bearing. And then length is 1.5 and 4 micro Reynolds, 410 Reynolds is what is mu. So first thing what I need to find out would be what would be my pressure. Pressure is nothing but load by 2R. This is the projected nominal pressure is load divided by projected area, right? This we know. So this is nominal pressure is pressure divided by projected area. Let me do this. Okay. Now what I want to do is I want to find out W. So P by W 2RL. Let me just find out what is that. Let me first do this. Shift enter. Okay. Then what we do is we find out this. So this is your 222 is PSI. 222 PSI is your nominal pressure. And there is only journal is rotating, right? So if journal is rotating, N is NJ, right? So nothing wrong with that. I basically go ahead and say my revolution is 30 per second. 1 plus. NJ is 30 revolutions per second. So basically, I have mu NJ by P R by C square. So basically, go ahead and let's find out what will be. And then what I do is I do this. So my Sommerfeld number comes out to be 0.135 and L by D ratio is L by 2R, which is 1. So now whatever I have to find out, I have to use these two numbers. The first one will be S is 0.135, right? S is 0.135. And then what else do I need is I need S and I need L by D. And L by D is equal to 1, right? So what I'll do is now I'll stop this and then we'll keep on doing other things. Let me unshare this. And let me share my okay. Right. So now we have these two things. We have Sommerfeld number we find out was 0.135. Sorry. .135. And then L by D was 1. So I have to find out the first thing what I want to find out would be H naught and E. So let's go back to H naught and E. Okay, this is what we have to find. So our actual thing is our S is 0.135. So 1.135 is roughly this. Sorry, my mistake. Let me just go ahead and draw this. It will be somewhere here. and our L by D is 1. So this will be, so H naught by C will be something like 0.42 or something, 0.42, right? H naught by C is 0.42. And then let's go ahead and look at eccentricities. The eccentricity we go roughly 0.58. So eccentricity is what you get is epsilon is equal to E by C. E by C is equal to, I'm sorry, this is acting out today. E by C is equal to 0.58. So I can find out basically H naught would be 0.42 times, what was C? If you remember, C was 0.0015, 0.0015, and E is 0.58 times 0.0015, both in inches. This is also in inches, and H naught is also in inches. Okay, because they're using this chart, which is kind of inches chart, unfortunately. Okay. But let me just go ahead and see what answers we get. Exactly 0.42, 0.00015, which is 0.00063 inches, or they call it, it's actually called 0.001 inch is called thou. That's what the machinists use, thou, 1 thou. So it's less than a thou, right? It's less than half a, it's actually slightly more than half a thou, which is very, very small. Half a thou is really, really small. And if you want to see, this one is your E is 0.58, 0.015, which is 0.000087 inches. That's the eccentricity between the shaft, the center of the shaft and the center of the sleeve have roughly this much difference. This is the eccentricity. If eccentricity is not there, there will be no pressure built up. Note that this is essential, just to let you know, because fluid has to flow in converging gap. Otherwise, this pressure buildup will not be there. So this eccentricity is required. Okay. The next thing what we have to do is you have to find out the same parameters. For that, what you have to do is you have to find out what is the coefficient of friction. Let's go ahead and find the coefficient of friction. Again, let's go there. Coefficient of friction is this. So we have this. We have coefficient of friction is 0.135. Oh, I'm sorry. We have this some. Go. L by D is equal to 1. This is roughly 4. R by C, if I go ahead and find out, this is what it is. No, my mistake. My mistake. L by D is 1 is this one. This is L by D is equal to 1. So it would be somewhere like this. 3 point something. 3.4 or something. 3.4 or something. So let's go see what R by CF. 3.5 roughly. So RCF is equal to 3.5 is equal to is equal to 3.5. So I can find out friction. So friction is nothing but 0.007. If you do all the math, you know R is 0.75 and C is 0.0015. So you can find out coefficient of friction is nothing but 0.0070. Now if I have to find the torque and the power, so I know that coefficient of friction times W is the frictional force, right? That's the load. So this is the frictional force. Frictional force. Now, torque will be nothing but frictional force times the radius. So I can find out torque is equal to FWR. FWR. And then I know that torque times RPM would give me some sort of a, this is in actually FPS units, you should not worry about it. I'll try and give you as far as possible SI unit problems when I do it in the exam, but just for demonstration, since I had these charts, I showed you this, but I also have charts which are so these are dimensionless charts, so they should work for any units. Okay, so you should not worry about these things. So I'll give you the units, all the units in SI in the exams or in the homeworks. I'll try to give you SI units. Okay. So from torque I can find the horsepower. So I think this is where we want to end, and then we can also find out the maximum pressure from different chart. Let me just go ahead and share the P max. Where do you find it? P max by P. You can also find that also if you want. This is the P max by P. No. Yeah, this is the P max by P. So you can again go 0.135 here, and L by D is equal to 1. So somewhere here. And then you can find out here. So it should be 0.44 or something. P by P max. 0.42. So you can find out what will be the 529 psi is the P max. Okay. And you can also find out what is theta P max, that also is there. Where does the maximum pressure occur? Where is the theta P max one? I see phi here. Okay, looks like that chart is not there, but I'll show you. 12.22. I may have it somewhere. Okay, sorry, looks like it is not there. I'll just pull it up for you from the book. Just 1 second, let me share the book with you. Yes. 12.22. So these were the charts which I showed you right here. These are dimensionless charts, so these will be independent of your any units, but I'm just trying to use some units because the ones which I had, I used it. Sorry. So this was the chart which was not there with me. Just 1 second, it will show up in your screen. Yeah. Let me just blow it up. This is the chart for theta p max. Again, you start from you're at 1.14, so you can find out how the chart, how the position of, so terminating angle theta p0, the position of the film, and the position of the maximum film thickness, both are given here, right? So you can find out either. So the black dot, this black dotted line is theta p max, which you have to look at from here. The open circle, the full dots are here. What do you call it? Open circle and the dots. So the open circles are theta p0. So open circles are for this one, and the complete dots are for theta p max for this side. Okay, so both these are superposed here. So you can find theta p0. It was not there in my lecture notes somehow, but these are the things where you can find out where the film starts, where the film ends with these graphs. Okay, so now I think this is finally over. I think that's it. Officially over with this. So theta p max and that. Okay, so that said, what we will do is we are already 3 o'clock. I have 10-15 more minutes. So there are a couple of announcements which I want to make. The first thing would be that I want to have the second presentation of what you have done on 11th. So is that okay? I'll send out an email today. And the final presentation I want to do, final presentation and the submission would be done on preferably on 30th November. How does that work? After your exams. I think when does your exam end? Anybody?
29th, sir.
So when do you want it?
28th or
So when do you want it? Do you want it 3 days after the exam? 3 days will be good enough for you? So I can do first or second also. I think the grade submission is not until I think submission of grades. I will just check when it is.
Some of us have placements on from first
So
December.
I'll need some time to make sure that I have enough time to grade. That's one thing which I need. Let me just go ahead and see when is the grading time. Then I can make some comments and give you some more time once you have, if I have grading time enough. Academic calendar for 2021. Let me just see. Grades are due. On the grades. Online submission of grades is when? Last date of submitting application 15/12. 13/12. So 13 is last day of submission of. So I have to show the answer scripts by 9/12 and 9th of. So that's fine. I think that should not be a problem. So I can do even 3rd of 3rd of December. That should also be fine. Does it work? Third December, does it work or you want more time? For project submission and also presentation.
In the first week of December, there will be like the placements for a lot of us.
So then you tell me what you want to do. You want to do it in the semester? I'm okay with it. You have to tell me when you want it. If you want to do it before that, I'm okay with it also. I have no issue.
If I discuss in the group and tell you by tonight?
Yeah, because I want to freeze it.
Yeah. So if
last class I wanted to ask, you were not there, so I was not able to contact you. But this has to be frozen. When do you want to do it? You let me know. If you want to do it in the semester, that's also fine with me.
Yeah. Okay, sir. I'll discuss in the group and tell you.
So when does your placements begin?
So just after the exam, like immediately after the exam.
So ideally you guys would want before the exam, right? This presentation and the submission also.
Yeah, maybe, but I'll discuss and tell you by tonight.
Sure. So give me that so that I can communicate it. But your final in-sem presentation would be 11th of November. I think that is the Thursday class, right? So we'll have a presentation during the Wednesday when you meet your TAs, right? We'll have a presentation with all the TAs present. You present whatever you have done up till now.
Okay.
So that's what I expect you to do. Any other questions you guys have about this or something else? Midsem, I'm still grading, so I'll finish it. As soon as I finish it, I will give it to you, the midsem thing.
Yeah, okay. So one thing, apart from MS Teams, can you also upload the lectures on YouTube?
I'll do that.
Yeah.
MS Teams, it's already there on the. If you go to the class thing, right?
It's there on MS Teams, but to view the lectures, you have to download the whole lecture.
On the YouTube also. Whatever is pending, I'll go ahead and do it.
Yeah.
No issues. Okay. Anything else you guys want, or you have any questions about what we have discussed today? Because gears you have already done in your class, right? In that in your KDOM you have done gears, right? Or no? Yes or no?
No, so because of COVID, we couldn't complete the entire portion of it.
Oh, so you haven't completed the entire. Oh, I forgot about that about KDOM. So what I will do is I'll cover cursorily about the gears. Next class I will cover cursorily the gears. I wanted to just share the basic concepts which you probably mostly know, but I'll still cover it. So that's the plan. I wanted to teach a little bit today, but then it's already towards the end of the class. I don't want to begin it today. So next class we will do gears. Okay, that is the plan. So if you have any questions, any concerns, anything you want to discuss, I'll be happy to discuss now. Okay. I just wanted to get a sense what, because last time when I was teaching gears, the students said that they have covered everything about gears in KDOM. So I had to quit it midway actually. Half the class I taught and then they said, oh, we have done everything, so we don't need to do it again in design. So any other questions, any concerns, anything you want to talk about your projects? Everything is going fine in projects? Any concerns about your projects? I'll be happy to talk to you. So this time I would like to see substantial progress, some analysis and solid models also, right? Some significant progress I would like to see towards your project. So I'm assuming everybody is working on the project. The project is 50% of your grades. So I expect you to take it very, very seriously. Okay. So I'll wait. I'll stop this thing. I'll stop the recording. And then if you have any questions, I'll wait for another few minutes. You can fire away. If you have any questions, anything.